more. So the talk about today is taking an example of a language model and how you can fine-tune an inference using ONNX Runtime. So we are going to compare its performance with PyTorch and show you how the ONNX Runtime is better compared to the PyTorch. And we'll also go through the technologies involved for training the language models. So what we are going to start with is ONNX Runtime. It will include both ONNX Runtime training as well as inference, and so show some of the recent benchmarks. Then we are going to talk about other technologies like DeepSpeed and LoRa, and then the environment setup and the language model which we are going to use today would be the Phi2 model. Then we are going to aggregate all of this together and see how we can use all of these technologies and use this in a simple way to run it on AzureML. After that, we'll go through the performance comparison for both training as well as inference. And if we have time, we'll go through the code walkthrough as well. So let's start with the ONNX Runtime. As Yusheng and Kunal has already spent a lot of provided a lot of benefits on using ONNX Runtime. I'm going to be brief here. So ONNX Runtime is a cross-platform machine learning accelerator, which you can use, which has a very flexible interface to use based on the model which you want to train and inference on. It can be used with multiple frameworks, including PyTorch, TensorFlow, scikit-learn, and much more. It has been trained in Python, and you can deploy it with multiple APIs like C#, Java, JavaScript. And you just need to convert your model to ONNX format, and this can be done with very, very few lines of code. So it's very easy to start with. So starting with ONNX Runtime training, it's used for training large models to accelerate training as well as reducing compute cost by either fitting your larger models into smaller GPUs or training your model faster. So we have support for CUDA as well as ROCm acceleration, and we also provide on-device training. It is built on highly successful and proven technologies of ONNX Runtime and ONNX format, and we get faster training by optimizing kernels up to 2x speeds for state-of-the-art models. And we can support larger models as well. For example, GPT-2 doesn't fit on a 16 GB GPU for PyTorch, but we are able to support it with ONNX Runtime. It's part of the ONNX PyTorch ecosystem, so you don't need to do a lot of work here. It's part of PyTorch via Torch ORT, and also part of Azure Container for PyTorch, which is our environment, which I'm going to talk about later. So here are some of the results for comparing the performance of various models. Some of the models are like Llama 2, Mistral, and other language models, and some of the models are also vision models like Google VIT. And in most of the cases, you can see the performance of ONNX Runtime with DeepSpeed Stage 1 is much better. And we can get up to like 3 or 4 times improvement over the PyTorch version. Let me now talk about the ONNX Runtime inference. It's also a high-performance engine for deploying ONNX models to production, and it has been optimized for both cloud and edge scenarios. And as Yusheng already mentioned, like it has been deployed. So the APIs which you can use are a lot. Like for example, you can use it with C, Python, C#, Java, JavaScript. It integrates with multiple hardware accelerators like CUDA for NVIDIA GPUs, ROCm for AMD GPUs, DirectML on Windows, and many more. And you can find most of this information on onnxruntime.ai website. And for ORT inference as well, we have seen a lot of performance improvement compared to models here. So here we are comparing, for the first 5-6 models, we are comparing the Torch script, the Torch 2, and ONNX Runtime. And in most of the cases, we are seeing like more than 2x improvement compared to the Torch script and Torch 2. The last 4 scenarios compare the Torch eager mode, the language models which we have, the Llama 2, and the Mistral model. So here we are comparing Torch 2, eager mode, then Torch compile, and the ONNX Runtime. So for these scenarios as well, we can see a lot of improvement compared to both PyTorch eager mode as well as the Torch compile. So one of the technologies which has been used a lot in the recent past is DeepSpeed. So DeepSpeed, especially for training, involves zero. So zero stands for zero redundancy, and it has three stages. So first of the stages is like, uh, so since the GPU memory is limited, the main aim of DeepSpeed is to reduce the GPU memories. And what it does is it partitions your memory and store your different states across different GPUs. So for example, for stage one, it uses the optimizer states and divide it equally in the different GPUs and use it during your training. So the memory usage on each of the GPU reduces. Then stage two, it takes stage one plus reduce the gradient states across all the GPUs. So again, your memory usage on each of the GPUs reduces. Then for stage three, it partitions all the parameters you have on of the entire model and partitions across different GPUs. So ultimately, you are reducing your memory in each of the stages. So each of the stages are more complex, but gives you added beneficial benefit of training a larger model on a smaller GPU. So using these optimizations, you are able to train up to billion as well as trillion parameter model on smaller GPUs. So these are the benefits of using DeepSpeed. Another technology which has come in the recent past is the LoRa, which stands for low rank adaptation, and it is a fine-tuning technique in which you use in which you freeze the bottom half of the model and try to fine-tune the model based on only the some portion of the model. So here you are using a lower rank matrix to just train a portion of your model. So you don't need to have like compute all the training weights, all the gradients and everything. So that helps you in faster training and faster uh, have lesser memory requirements. The memory requirements is lesser because you are only training a portion of your, retraining only a portion of your model. It has similar inference time because the model is not changing. The size of the model is still the same. And it is easier to switch tasks because what you can do is with LoRa, you can retrain your model or fine tune your model on different tasks. And you need to just switch those different parts of the model for different tasks. And it will help you in optimizing your, like reducing your memory requirements, the model parameters and everything. So next comes as the Azure container for PyTorch. Here, what we have is an environment which you can use and not worry about the environment setup, whether it works with different kind of GPUs or different kind of platforms, what CUDA version you are using. You don't have to worry about those things. We have already pre-built a lot of environments with the latest PyTorch versions, with the latest CUDA versions and ROCm versions as well. And you can use this optimized training framework to run and train your machine learning workloads. So it helps you, like we have the latest compatible versions of Ubuntu, Python, PyTorch, CUDA, etc. And then it already contains all the latest technologies, including like the ONNX Runtime mixture of experts, DeepSpeed, Nebula, MSQL, and others. And it is very much integratable with the Azure platform. So you can use it on AzureML and use it to train your models, fine-tune your models, and more. It's basically a Docker container for your large distributed workloads. So a lot of 1P and 3P customers are already using ACPT for training their workloads. One of the examples in which Fashionable, which is a small company, used our ACPT container to train their models faster. They were facing a lot of issues with multi-node training, and because there goes a lot of things to create an environment which is compatible with the different GPUs. And while using ACPT, they were very quick to adapt to it, and they were able to train their workloads much faster. So the model which we are going to use today would be the Phi-2 model. So Phi-2 model is a recent model, as you might have heard about it. It's a 2.7 billion transformer-based model with next work prediction objective. It has been trained using mixture of synthetic and web data sets. And the training time for this model was very, very small. It just took 14 days on 96 A100 GPUs. So you can see compared to other like Llama and ChatGPT and other models, the training time was very less, but it has a performance uh, like comparable to other models as well. This is just a model which we are taking today to showcase our improvements and performance benefits. But ONNX Runtime supports a lot more models, including the Llama 2, 7 billion, 13 billion models, Mistral 7 billion models, vision models from Microsoft and Google VIT, and so on. And we also support like stable diffusion, Falcon 7 billion models, and so on. And most of the models, we get better performance, easier integration with very few lines of changes, and you get these additional benefits. So let's talk about how does it all comes into the picture and how you can use this for your training workloads. What you start with is a hardware. Let's say you want to start with a V100 or A100 GPUs, or you want to use ROCm GPUs for your use case on AzureML. And then you can use the training methods which you want to specify. For example, if you want to use the SDK, or you want to use the command line interface, or if you want to use the UI, which can be done using AzureML Studio. Then what you need is you have the hardware, you need an environment to run your code on. So the environment which we are using here is the Azure container for PyTorch, which already contains the latest versions of PyTorch, Python, Ubuntu, CUDA versions based on the GPUs which you're using. And it also contains all the latest technologies, including ONNX Runtime, DeepSpeed, MSQL, which is a variant of Nickel for faster communication between GPUs, then the ORT mixture exports, and many more things. So using this as the base image, you'll add your scripts for fine-tuning your model or training your models, whatever case you have, and you'll specify the compute targets, which will be like the A100 GPUs or H100 GPUs, and specify your jobs. And once you have an output of the model, you can retrain your model. And once your model is finalized, you can deploy these models using the ONNX format, convert into the ONNX format, and use the ONNX Runtime Inference to deploy your models for your faster inference. So the benefits of using AzureML is that it is very easy to set up with the ACPT. It is cheaper, faster training, as well as the inference with ONNX Runtime is much more faster. So you don't have to worry about your environment setup. You can deploy on GPU and mobile with ONNX format models. It works with your code. Whatever code you want to bring up, you can add and modify it. And it works with the AzureML Studio here. So next, I'm going to talk about the performance comparison for the Phi-2 model. This is for the V100. We ran the Phi-2 model on 8 GPUs. There are two ways we did the training here. The top table contains the results without the LoRa, and the bottom table contains the results with LoRa. So without LoRa, with different batch sizes, I have put the seconds per iteration numbers. For PyTorch and Torch compile on V100, we got the very similar results. And as you can see, with higher batch sizes, up to like a batch size of 5, the PyTorch is going out of memory. But with ORT training, you are able to run it. So there is additional optimization parameters you can specify to run your models faster. For example, ORT training provides the Triton optimizer to run your model even faster. And in this case, for Phi-2 without LoRa, we are seeing a performance improvement compared to PyTorch and Torch compile. We are seeing 10, 11% for batch size of 2 and 3, and we are seeing up to like 50% improvement compared to batch size of 4. With LoRa, as I mentioned earlier, for fine-tuning parts of your model, we are getting even better performance. And here also, we are getting similar numbers for PyTorch and Torch compile. And compared to PyTorch, for ORT training plus Triton, we are getting performance improvement in the 20% range for batch size from 2 to 4. So as you can see here, the performance is really good. And it matters a lot because in training, you will be spending a lot of time on your compute, and it will save you hundreds and thousands of dollars based on the use case you will have. These are performance comparison numbers for A100, and these numbers have been generated using only 2 GPUs. Here we were seeing slightly better performance for PyTorch in Torch compile world compared to PyTorch. So I have linked these numbers, compared ORT training with respect to PyTorch and ORT training plus Triton with respect to Torch compile. And I have listed the results. These are without LoRa. And here we can see performance numbers improvement ranging from like 16, 17%, and like up to going up to 20%. So as you can see here, even on A100, we are getting a lot of good performance compared to both PyTorch as well as Torch compile. One thing to note would be ORT has slight overhead compared to PyTorch. Sorry. This comes primarily because of the conversion of your ONNX model, converting your PyTorch model to the ONNX format. But your training time is usually in like minutes, in hours or more. But the training, the overhead which we get for the ONNX runtime is usually less than 100 seconds. So the overhead is not significant for the overall training which you do. So overall, whatever fine-tuning or the training you are doing, you will getting a much better improvement here. Now, this is the performance comparison for the Phi2 model, and it compares ORT versus eager mode. So the first, the light blue one is ORT versus eager mode, then the dark blue is ORT versus Torch compile, and the third is ORT versus DeepSpeed, the purple one. So the difference between a standard PyTorch inference and what we are doing here is we converted our model slightly differently. So what we noticed was we like in Phi2, if we only keep the last 3 layers as FP32 and convert all the remaining layers to FP16, we are getting very similar accuracy to PyTorch. So that's why we are doing this conversion. And here we can see the inference numbers are only using single A100 GPU. And you can see we are getting up to like 15x performance compared to Torch compile, and up to 6x performance compared to eager mode, and like approximately like 7x performance compared to the DeepSpeed number. So as you can see here, we are getting a lot more benefits compared to both PyTorch and Torch compile for the ONNX runtime inference. So a lot of times what we have the issue is like our GPU memory is limited and you want to train a bigger batch size. So in this Phi2 case, we were getting out of memory with batch size of 6 and higher. So what ONNX runtime provides you some kind of training guidelines which you can use to even run like models sometimes faster, for example, using Triton optimize the Triton backend. And then there is another thing called memory optimizers for ONNX runtime training. So what it does is it does a subgraph recomputation for using your memory efficiently. So for example, what it does in this case is, so it will look at your graph, convert it, and it will see where are the optimizations possible in your graph. So in this case, when I added some of the optimizations plan, for example, here I'm adding a cast optimization plan, which you can retrieve through like running some of the guideline options here. And when you add that step, I was able to run like a batch size of 6 for Phi2 model, the entire model, With adding one more optimization plan with cast and fast GLU, I was able to run a batch size of 7 and added a fused math multiplication optimization as well. I was able to run a batch size of 8. So you might be able to run higher batch sizes, and sometimes you have a constraint that you need to run a minimum number of batches. So you can achieve higher, you can achieve to fit a larger model on a smaller GPU. So the details of running a memory optimizer can be found on this link. There are more guidelines available to run your ONNX Runtime training, and which can be found on the second link. And I've also provided a way to reproduce whatever we did comparing the PyTorch and the ORT training, and I've put that in the third link. So this is, you can find everything here. I think like we are slightly running low on time, so I'll skip the code walkthrough, but it's very simple. It's using Hugging Face libraries, for example, transformers, optimum, and so on. And that's why I've put all the code on the ONNX Runtime training examples. You can also find more examples on ONNX Runtime inference examples to run your use cases. And if you have any questions, you can reach out to us through the GitHub repos. And yeah, so today we talked about the ONNX Runtime, why to use it, like how it helps in efficiently training and inferencing. We also talked about the different environments which we use to reduce time for your setup, as well as how it is easier to use. We also talked about small language model and large language model fine-tuning and inferencing. So let me know if you guys have any questions. Thank you.